Hey everyone, welcome to, I believe, lecture number 16. Hope things are going well where you are. So we'll go ahead and get right into it. We've got a lot to cover today. Let's start with some announcements. So I will hand it over to Aravind for a couple quick announcements.
Hello everyone. I see that many students are not on Piazza interacting themselves. So interacting on Piazza accounts for 10% of your grade. So I request everyone to post questions, answer them, view the questions and all that part. And the second one is I still see that three groups have not booked their slots for this week's meeting. Please book your slots for tomorrow. None of them are available today. There are three available tomorrow. Please go ahead. And group meetings will be held every week for 6 out of the 12 groups. So please check the schedule and book your slots for that week. That's it from my side, Professor.
Wonderful, thank you, Arvind. And yeah, just a reminder that 10% of your grade does come down to participation. In previous years, there has been kind of an in-person component to that, but now since we're doing fully online, we are fully grading your participation by Piazza. So please do spend some time in Piazza. If you don't have any questions, then maybe you have some answers, right? So hop on there and see if you can help out with different answers. So we are expecting you to contribute to Piazza, whether it's through asking questions or through answering questions. So please do that. That is a part of your grade. And then also, yeah, for groups, please sign up for your meetings. We are looking forward to meeting with you, so do get those meetings scheduled. Just email us if you have any questions or concerns about getting that set up. Okay, Rohan, any announcements from you?
No, Professor.
Great, all right, good deal. Okay, well, let me go ahead and get a screen share going. We've got a lot of cool stuff to cover today, so I want to go ahead and hop into it here. So first of all, here's our schedule. Let's kind of see where we are here. So we've made it to October 29th. So this is our last lecture on self-driving cars, and we may start a little bit of PyTorch today. We'll see if we have time. And a reminder, you have some stuff due soon. So the programming challenge is due Monday night at midnight, and the quiz is on Monday. And again, this programming challenge is the hardest of the year, so do make sure you're working on that. If you start on Monday or something, you might be doomed. We do give you some grace days, so if you submit it on Tuesday, you lose a point, I think, something like that. So, but please do not wait until too late to start. We also are anticipating that if a lot of you guys wait to submit, there may be some server issues. We'll try to be nice about that. So if every year, someone says, "Oh, hey, I submitted my code at 11:50 and the server was slow," so we try to be nice about that and helpful, but sometimes we have to say, "I'm sorry, you should have submitted earlier," right? Because yeah, it's due at midnight, but there's other considerations we would like you to take into account. I just realized that I'm kind of absent-mindedly clicking around here, which is probably making my screen share a little distracting. But anyway, please do start on that early. Let us know if you have questions. Come to the TA's office hours. Email Arvind and Rohan. I'm here to help too if needed. And yeah, the scikit-learn library, it's a great question. You are able to use OpenCV, and yes, because you're allowed to use the optimized package. So yes, you can use scikit-learn, OpenCV, pretty much everything except for the deep learning libraries is what you're allowed to use. So yes, you are allowed to use scikit-learn, and the reason you may use that is because of the optimization library. Oh, I'm sorry, that's SciPy. Thank you, Hernan, my mistake. So can we use scikit-learn? Does scikit-learn have a neural network? Probably not then, actually. So yeah. Okay, yeah, so no scikit-learn. Sorry, guys. Thank you for asking. Yeah, no scikit-learn. That should be in the documentation. We should list the libraries you're allowed to use, and scikit-learn should not be one of them because it includes neural networks, and the whole point of this module is that you write your own neural network. Thank you, Arvind. Yep, so NumPy, OpenCV, TQDM, Time, and SciPy. Those are your allowed libraries. Sorry about that, I got SciPy and scikit-learn confused. SciPy is the one you're able to use. Scikit-learn, you are not. Okay, any other questions, guys, before we hop in? All right, and as usual, feel free to hop in as we go. Okay, so let's pick up on story time here. So last time we talked about this ALV thing and about how the very first autonomous car kind of worked. And it had some really cool engineering components to it, and it had some parts that didn't scale too well, but we're not too surprised. It was the very first autonomous car. It was back in the 80s, and it's cool to see what they did because it can help us figure out other approaches and maybe hopefully more successful approaches. So we left off kind of in the late 80s, and then I told you this kind of crazy thing, which is that in 1995, 25 years ago, these two researchers, Todd Yoakum and Dean Pomerleau at Carnegie Mellon, they drove 98% autonomously across the US in this retrofitted van, which is pretty cool, right? So how did they do this, right? So in today's lecture, we are going to discuss how they did it. So this should be a cool lecture. We're going to get into a lot of math, as you can imagine, or more coding, I guess. But as you can imagine, neural networks are involved. That's a big theme in this module. So let's get into it. Let's talk through the story. It's really cool. It's really interesting. Okay, so as I mentioned, the ALV machine that we talked about last time, that huge giant, let me just pull up a picture because the picture is so great. How can we not look at this picture? Where is it? I love this picture. There, yeah, that is cool, right? So there's the ALV. It weighs 15,000 pounds. You can see the camera. This is kind of like a video camera, you know. That is the ALV. It drove 2 miles an hour. Actually a little slower, I think, very slow. But it really was the world's first autonomous vehicle, which is pretty cool. So this was supposed to be like a test bed. When they got funding for this project, the government said, okay, you know, other researchers can come to Colorado, which is where this project was, I believe, and they can test their algorithms on the ALV. That never really worked out for a number of reasons. That's hard to do. When you're researching this kind of stuff, it really helps to have your own robot, to have your own hardware. So that's exactly what Carnegie Mellon did. So Carnegie Mellon, they were also able to get some funding from the US government. They received around $1.2 million of funding from the same strategic computing initiative in the 1980s and 90s. And they made this really cool van. So they made this, they call it the Nav Lab, and they made this van that they could use to develop self-driving algorithms. So let's talk about it a little bit, and we'll talk about this van a little bit later and share some of the, I'll show you a video and stuff like that. But this was called the Nav Lab. And what I really want to get into though is this, because this is really the heart of today's lecture, and this is what I want you to really start thinking about. So we spent, you know, a good 30 minutes last time discussing how the ALV, the first generation autonomous vehicle, how it saw the world. And if you remember, we talked about how the researchers really just did this, they did this red-blue color space thing where they took the blue color channel and subtracted the red color channel, I think. I mean, it might have been blue minus red or red minus blue, I can't remember, but they took a difference of the two color channels. And doing that allowed them to pick out kind of the road from the rest of the world, because the road turned out to be more red in this case. So that was their approach, and there's a few steps they did that I didn't mention. So there's some other math that was involved. So after finding the road pixels, they did a computer vision technique where they found the boundaries. They probably used an infilling method. We don't cover those techniques too much in this class. There's lots of good documentation in OpenCV about how to do this. If you're curious about that, I would recommend checking out the OpenCV documentation. We haven't talked about the library OpenCV too much. We'll talk about it at some point, and we'll use it here and there. But this library, OpenCV, has some great methods for filling in and finding borders and things like that. OpenCV is not really a machine learning library. It's more of like an analytical computer vision library, and we'll talk more about that later in the course. So they did this, right? The next thing they had to do is actually a projection. So this is a 2D image, and they needed to know where to drive in 3D space, really, all right? So this is a whole set of mathematics. We're going to cover this in Module 7. We'll talk about how to do projections like this. So they took this, you know, mapping of the road, these boundaries. They projected a 3D space, which again is just some more math. And then finally, they use what's called a controls algorithm. So if you've done any robotics, you may be familiar with controls algorithms. Basically, it helps you figure out how hard should I turn my steering wheel to reach my desired output angle to keep my car on the road. So again, more math, right? So this is the pipeline that the ALV team built. And there's like 4 or 5 steps, something like that. And this is how it worked. So at Carnegie Mellon, around the same time, a graduate student named Dean Pomerleau, he showed up for graduate school. And he thought about this problem a little bit differently. He had a very different approach. And the way I like to introduce his approach is just a big old picture like this, right? So the previous method, again, you have an input image, and then you do this thresholding thing, then you do boundaries, then you do projection. It's a bunch of math, right? So what Dean Pomerleau said is, okay, let's just treat this as one big block, right? So you've got an input image, you're going to do some math. You know, the input image, as you know, it's just numbers, right? So it's just pixel values, just numbers, you know, a bunch of numbers. And the output, and I'm just thinking about steering right now. So this was the main first focus in autonomous driving, it's called lateral control, steering the vehicle. Of course, if you're going to drive fully autonomously, you have to do gas and brake as well. And we'll talk about that a little bit later, but really we're going to focus on steering. And if you just focus on steering, it's kind of an elegant little math problem, right? Where I've got this image that has a bunch of pixels that are just numbers. I've got, you know, let's say 1,000,000 numbers. If I have a 1 megapixel camera, if this is 1,000 by 1,000 pixels, for example, that'd be 1,000,000 pixels, 1,000,000 numbers. And then if it's color, you got some more, but that's fine. But really, if you are trying to build an autonomous car, like this is the math problem you have to solve. Hopefully that makes sense, right? So that's the math problem you have to solve. You have to say, okay, based on all these input numbers, which is an image, where should I steer the vehicle? At what angle should I turn the steering wheel? That's what you do as a human, right? When a human sits down to drive, you see an image like this, and then you decide, oh, I think the wheel should be at this angle, and you turn at that angle, right? You're not thinking, hey, it's 3.7 degrees, but that's really what you're doing, right? So if we think about the problem like this, then it might lead us down an interesting path. And the path is this, basically. It's, if that's the function that we're interested in, is it learnable, right? Can a machine learning model, can it learn that? Can it learn the mapping, the math, that goes from images to steering wheel angles? So I have an embarrassing story that I'll share with you just briefly. So when I first got into autonomous driving, you know, I worked in this field for about 2.5 years, something like that. Maybe let's see how video. Okay, yeah. So when I first got into autonomous driving, I've got a weird camera view today, but when I first got into autonomous driving, I had a discussion with a coworker about exactly this problem. So it was, you know, is this learnable? Is this a learnable function? And I kind of argued that it might not be. I said, I don't know, like we can't prove that. That seems ridiculous. And I didn't know about this research back in the 80s. And I was totally wrong. My coworker thought it was possible. I thought, I don't know, maybe not. But it is possible, which you'll see in your programming challenges, in fact, to do exactly this. So it's pretty cool, because if you think about it, we'll get into this in more detail. Sure, there exists some function that can map from these pixels to the steering wheel angle. There's some function out there in theory, but if you're going to learn that function, your only training data, which we'll get into in a second, is going to be the steering wheel angle. Like that's your only training data. Like that's crazy. Like just learning that whole function just from the steering wheel data, that seemed impossible to me, and it still seems kind of like a miracle. And we'll get into it here in more detail. Okay, so this is Dean's original paper from back in the 1980s. This paper is very readable and very good, and it might actually help you on your programming challenge, so I'd recommend looking at it. It's a great paper, and it's got a lot of good ideas that are very relevant to your programming challenge. So I want to go ahead and get us in right now, so let's get cracking. I want to go ahead and do a little poll, so if you guys can get that ready, that'd be great. Thank you so much. So let me introduce the question, then we'll open the poll. So this is a figure from Dean Pomerleau's paper from the 1980s. So his idea was to use a neural network to steer a car. That was his idea. And it's interesting, at Carnegie Mellon at the same time, Geoff Hinton, who you remember is kind of the inventor of this back propagation technique we use to train these things, he was at the same university, and they apparently had conversations. So Dean Pomerleau didn't think of this all by himself. It was partially by collaborating with and discussing with Geoff Hinton, I think his research group, which is really interesting, right? Really cool. So this is a representation of the neural network that Dean Pomerleau used to drive NavLab, to drive that car. The input is an image. It's been downsampled pretty far, so it's only 30 by 32, and we'll do something similar shortly. So it's a very low resolution image. Now, look at this neural network with me, right? So let's look at it carefully together. So throw it in the chat window if you know. How many layers deep is this neural network? How many layers deep is this guy? So a lot of people say 1. I would say 2. I would say 2. It's very similar to the neural network we used in the Neural Networks Demystified series, and that one had 2 layers. Because think about how many weight matrices do you have to have? You have to have 2, because these first connections are 1 weight matrix, and these are another weight matrix. So yeah, Hernan, that's fine. What I'm really getting at here is that how many sets of weight matrices do you have to have? And you have to have 2, because we have 2 sets of connections, basically. This is a 2-layer deep neural network. Now, another thing is, I asked a lot of you guys early on, I said, does this challenge, just solving this, right? Does this feel, and I'll go ahead and ask you guys again, throw it in the chat window, please. Does this feel more like a regression problem or a classification problem? What does this feel like to you? Yeah, so everyone says regression. Now come down here with me, right? So look at Dean's paper, right? If this was a regression problem and you were just predicting one variable, the angle of the steering wheel, how many output units would you expect? How many output? You'd expect 1, right? Abaji, yeah, perfect, excellent, yeah, Jagadish, good. But how many outputs do you see? You actually see 30, right? We'll talk about why he's doing this in a minute. You may already know. If not, that's fine. We'll talk about why there's 30 output units, but set that aside for a second. So what I want you to think about, and yeah, that's right, Subham, it's about bins. We'll get into that in a minute. The thing I want you to think about first that I think is going to really help you understand the solution and understand what you're building in your programming challenge, I want you to think, about how many weights, how many parameters approximately does Alvin have? And oh yeah, by the way, Dean called his neural network Alvin, and it stood for Autonomous Land Vehicle in a Neural Network. So a big acronym. This is called Alvin. So yeah, how many weights does Alvin have? How many parameters are we tuning? So I'm going to go on mute for a minute. If you guys can open up the poll, please. We'll give it 30 seconds. How many weights does Alvin have? Okay, thank you. All right, so it looks like we have F on there. That's interesting. So whoever said F, I'm not sure what lecture you're watching. I don't think it's mine. Okay, so the most common answer is C, and the second most common answer is D. Okay, C and D. So let's have a look here. Okay, so let's talk through it here. So I believe the right answer is C. I believe so. Let's talk through it. So they haven't drawn all the weights in this picture because it would be hard. So every hidden unit is going to be connected to every single pixel. Hopefully that makes sense. And how many pixels are there? There's around 900. It's 30 by 32. It's like 940 or something. So let's just call it 900 or so. So 900 or 960. Yeah, sure. Oh yeah, sorry, not 940, 960. There you go. So we'll call it 1,000 then. Thank you. You guys are paying attention. So if there's 1,000 pixels, that means that each one of these hidden neurons has 1,000 weights, because every pixel gets multiplied by a weight, and that results in the output value that gets added together. So 4 hidden units means 4,000 weights approximately. And the output actually has way less. So it has 4 hidden units and then 30 outputs. So 4 times 30 is like 120. So it doesn't really contribute that much. So the answer is around 4,000. So the answer is C for that reason. And we'll see all those weights in a lot of detail very soon. Okay. All right, so there's my official number right there, 3960. This might seem like a lot of parameters. I don't know, it depends on who you are. The ALV algorithm, remember, had 4 parameters, RGB plus a threshold. Modern deep learning networks have like tens of millions, so maybe it's not a lot, maybe it is. Excuse me. But actually, let me ask you a question really fast before we get into it. So we're about to actually code this thing in TensorFlow. Before we do, let me just ask you a question. I didn't talk about this earlier. How do you get training data, right? Like, you want to go train this thing. And just to make it clear, when you train your model, the input is the image, and the output, the Y value, is the steering angle. So like, how do you do it? So if you worked for an autonomous driving company tomorrow and they were trying to do this technique, how do you get training data? Any ideas? So Abhijit says sensors while driving. Yep. So you got to attach a camera to the vehicle. That's fine. And you need a sensor on the steering wheel, an encoder, right? But then what do you do? What do you do after that? You just drive. Yeah, it's a kind of a simple answer, right? But I want to point it out though, because what we're really doing, so in this video, you know, a human is driving this car. This is actually my boss at my old job, this guy named Tom. He's pretty cool. So he is driving the car, right? So sometimes this style of autonomous driving, which we'll get into if it's a good or a bad style later, but it works really well in some ways. So this style is often called behavioral cloning. Behavioral cloning. And it's called that because you're kind of trying to clone the behavior of a human, right? So that's the idea. And you can get a lot of data really quickly. Just drive, collect the data, and you can train. Okay, so let me pull in some real data. And this is data that was collected from my old company. Like I said, they were kind enough to let us have some data for this course. So I think that's really nice of them. So here's the data. Let me show you what it looks like. So here it's grayscale, so I'm showing it with that Viridis color map. And I've downsampled my data to 60 by 64. The camera is higher resolution, but I've downsampled it. You can choose in your programming challenge how much you want to downsample. These are the images, right? And these are the outputs, right? This is the angle that the wheel was actually turned at. So this is kind of a straight ahead road. The angle of the wheel is pretty small. This is a left turn. You can see a big negative number. This is an even sharper left turn. You can see an even bigger negative number, right? So you can get a feel for the data, hopefully. You know, the bigger the turn, the more negative the number should be. Okay, so here is a time series plot of our data. Here's the steering wheel angle as a function of samples over time. I believe this data is sampled at 10 hertz, just in case you're interested, but it doesn't really matter too much for this, this assignment. Now, I want to point something out. Look carefully at the data here. So you might see a pattern. You might see this little pattern right here. This repeats again here, and it kind of repeats again here, and it kind of repeats again here. It seems like there's like a periodicity of 3 going on. Like you see this thing happen, this thing happen, this thing happen, and then it kind of starts over. Why do we see this periodicity of 3 in our steering wheel angle data? Any ideas? Why is there a periodicity of 3? So yeah, same circuit, it's a track. How many turns are in the track? Any guesses? 2 is a good guess. It's 3. There's 3 turns. And like, maybe I should actually point down here. This is a better thing to look at. So when it's 0, we're kind of going straight, right? But this is actually turn 1. This is turn 2. This is turn 3 down here. This is the sharpest turn. And there's turn 1, there's turn 2, there's turn 3. So it's 3 turns. And here you'll see we're going to use some of this data for training and some for testing, which we'll get into in a second. Now let me go ahead and get into the bin thing. So something that Dean Pomerleau figured out back in the 1980s was that if he just did a regression problem and he had the deep learning model try to directly predict the steering angle, his model didn't learn as well. If instead he broke up the steering angle into different bins, then he could, the model would learn better. So I talked to Dean about this a little bit, and he thinks it has to do with making the problem more linear, which kind of makes sense, like small changes in the input result in small changes of the output. There's a whole thing we could talk about for that, but let's keep moving a little bit here. So what he did is he broke up all the steering angles from like you know, there's a bunch of steering angles that you could turn this thing through. Here our range is from like -150 to like 25 or something. So you break this up into even little bins. And then instead of just putting like a spike at the bin that the angle falls into, you put this kind of distribution around it. You kind of smooth it out. So it's detailed in the paper. And then I think the code to do it, like, oh, I guess I've already saved it here, right? Okay, you'll have to write that code in your challenge if you use this approach. But what we do is basically we put the center of the bin here that has the right answer, and then we kind of put a little spread around it. So by doing this, we're kind of making our training signal a little bit smoother. So like here, we've got this big negative number, so it falls in this bin. -76 must be this bin after we chop up all the possible steering angles into discrete categories. And then you add these numbers around it just to give it kind of a smooth behavior. So this is how Dean set up his training, and that's detailed in his paper in a lot of detail. Okay, so let's get into actually training this thing. Let's train Alvin here in 2020, 30-something years later. As hopefully you've learned in this class, when we do machine learning, it's very important to divide our data into a training set and a testing set. What I've done here is I've just said, okay, let's take 3 laps of driving data, 1, 2, 3, and let these be our training set, and then we'll test on a 4th lap. So that's the idea here, okay? So now we're gonna build Alvin in TensorFlow, and please ignore all my errors here. So I think I have an older version, I think my code is in an older version of TensorFlow perhaps, and there's a newer version out or something, but I think this is backwards compatible. So I'm gonna import TensorFlow running on my little MacBook here. And let's see here, great. So this is Alvin, and again, don't worry about all those warnings down there right now, but I'll go ahead and run this code. This is Alvin implemented in TensorFlow. So what's interesting that might be relevant to you guys, let me make this a little bit bigger, make sure you can see, okay? So what might be interesting to you, students who are working on the programming challenge, is that here is a solution to the programming challenge. And it's going to do pretty well. I think it would get you a 9 or a 10 on the score, depending on how we do in a minute. But why can't you submit this, right? Why can't you just copy my code? Does anyone know why? Yeah, so it uses TensorFlow. We're not going to let you use TensorFlow, and not because we're mean, just because we want you to understand how this stuff works. But in the next series, in the deep learning module, we'll be using PyTorch, which is very similar to TensorFlow. I'm just showing you a little bit of TensorFlow here. 2 years ago, this course was totally in TensorFlow, and then I switched it over because I think PyTorch is a little bit better placed for you guys to be. I think it's going to give you more options and flexibility. But here, this is a library called TensorFlow that lets you do deep learning really easily. But all I really want to point out to you, so I wouldn't worry about the syntax of TensorFlow too much, but the thing that I really want to point out to you is that this is actually the whole neural network. So the whole neural network fits in 2 lines of TensorFlow. And when we get into PyTorch, it's going to be the same kind of idea. So this is what's called a dense layer. This is a fully connected layer, like all the layers we've seen so far. And this is another layer, basically. This 4 here, does anyone know why is there a 4 there? What is that telling TensorFlow to do? It's the number of hidden units. Yep, thank you. Yep. So in Dean's paper, right, he used 4 hidden units. You don't have to use 4. You could try other stuff. I've tried 9 before. That worked pretty well. But yeah, he chose 4, so we're choosing 4. So that's 4 hidden units. That's where we're picking it right there. Anything else interesting here? I'm using a sigmoid activation function. Here's my loss function. I'm using the mean square error, just like we did in the Neural Networks Demystified series. Oh, and the very last thing, I'm using this Atom optimizer, so not the BFGS optimizer. Again, the Atom optimizer might be worth looking at on your programming challenge. I don't think you have to use it, but if you're trying to be competitive or if you have issues, you may look into it a little bit. Atom is pretty straightforward to implement. Again, this is a hard programming challenge, so you may have to experiment with techniques like this. I know some students have done this in the past. So there is a link to that paper if you want to look at that. Cool. So this is Alvin implemented in TensorFlow. I'm going to train it with a learning rate of 1 × 10⁻⁴. Tuning your learning rate is really important. So as you do your programming challenge, I encourage you to, this is probably the most important hyperparameter. If you're only going to tune one thing, try messing with your learning rate. Okay, and I'm going to train for 5,000 iterations. And I think I've made a cool animation. So I'm going to go ahead and run this cell. And as I'm running this cell, we should see our animation update. Yep, cool. So every 50 iterations, I'm updating, or every 25. And you should see this animation running. So the loss function is going down as we train. It's going to take a little while. My little MacBook is struggling. I'm not on my GPU machine today or anything. And is there anything I want to point out to you? Not really. This is just TensorFlow code. I wouldn't sweat it too much. I'm not going to quiz you or test you on TensorFlow, and you're not allowed to use TensorFlow. TensorFlow is a very popular deep neural network tool, though, so you may use it in other projects, other classes, other applications. So just keep it in the back of your mind, and if you're interested, you can certainly learn more. So we're still training. Oh, what does RMSE stand for? Anyone throw it in the chat window? What does RMSE stand for? Yeah, root mean square error. Thank you. Yep, perfect, great. I saw a question I wanted to see if I could address real quick. So Subham says, frustrating to try different learning rates as it takes 8 to 10 minutes to train. Yeah, Subham, welcome to deep learning. Yes, like waiting around for stuff to train just sucks. Yep. I agree, it is frustrating. I have that problem at my job all the time. Maybe try to train 2 models at once if you have enough compute power. But yeah, it's just that's just reality, unfortunately. That's where the technology is today. Okay, so yeah, this is root mean square error. This measures how well we're doing. And basically, the lower this goes, the closer Alvin is to steering like my boss, Tom, this is whose data we're training from. So it's still going down. This thing is learning pretty well, it looks like. So we're going to let it keep learning. We'll see how it does when it gets to 5,000, but it's training. My little MacBook, I don't know if you can hear it. Its fans are spinning. It's working really hard. Training, training, training. And yeah, this is just kind of the game of deep learning, sitting around. I will make a little comment. So, Subham, I'm really glad you mentioned this. It is frustrating waiting for this stuff to train. I just want to point out a couple of things. So, in this class, I try to really expose you to what real deep learning is like in production. I shouldn't say real. I should just say, I try to expose you to what my experience has been as a deep learning practitioner, right? Everyone's experience is different, but I'm trying to give you something close to what I've seen in industry. And yeah, waiting for these things to train sucks. Some of these models take days to train. Some of the models I deploy at work take a day, 2 days to train. And just a little comment, I highly, 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 highly recommend doing some kind of visualization like this while you're training. It takes a little bit more time, but what can happen is, you don't want to sit around for 10 minutes, like Subham said, or for hours, to see that your network didn't learn anything, right? So by doing a visualization, like, you don't have to animate it, you could make Hey guys, can you hear me?
Yes, Professor.
All right, we're on the hotspot. All right, we're gonna see what happens. I agree. I'm not sure if the video is gonna work. We'll try it. My power is still out. If this fails, we will postpone. So thank you for your patience. Let's try a screen share. We'll see if it's workable. If not, we'll postpone. Okay, so let's try a whole screen share just to see if my little hotspot can do it. I have a pretty good signal, but we'll see. All right, let me know if that's coming through.
Yes,
It is,
Professor.
Professor.
Okay, and you can hear me?
Yes.
Yeah.
All right, let's try it. Cool. The one thing I don't have is the chat window. Maybe I can do something like this, or let's try one more slightly different thing actually. Well, actually, let's keep going. We've lost enough time. Okay. All right, great. So yeah, the one thing I can't see is the chat window. We'll see how this hotspot thing does. I've got 50% battery on my phone. We'll try it. So while we did all that power outage drama, and I'm not going to try my video, that seems ridiculous. While we had all the power outage drama, the model did finish training on my little MacBook, which is great. I still have 100% battery somehow, so that's awesome. And yeah, the error went down, right? So let's go ahead and look at those predictions. And let me know, guys, if I lose audio quality. So here are the predictions. Here's the predictions for that model. So the blue line, this is the human, the blue line, right? And the green line, this is my boss, Tom. So, excuse me, the green line is the model, right? So you can see it's not perfect, but it's also not bad, right? So it's overall, it's matching the human not too badly. Notice, guys, that the human has kind of a nice smooth curve, and the model is more blocky, right? So I'm going to change how I'm doing screens here so I can see the chat real quick. Throw it in the chat. Why is the model prediction so blocky, right? Why does it make these discontinuous jumps? Throw it in the chat if you know. I'm just going to change my screen share. There we go. Cool. Yeah, so Prathim says bins, and that's the right answer. Yep, so it's the bins, exactly. So the binning means we can only predict discrete values. Yep, exactly. Okay, and is my screen share working now?
Yes, Professor.
Okay, wonderful. All right, the hotspot is doing great so far. All right. Okay, so this thing learned, right? So what I want to talk about now is how did this work, right? How was it able to learn to do this, right? How is this possible? So let's get into it. So this is probably one of my, I think this animation is fun. I enjoyed making this animation. So what this animation shows is a bunch of stuff happening as we train. So it's showing how our loss function is changing. As we just saw, this is the loss function. But it's showing a bunch of other stuff as well. So I want to get into that in detail. So I asked earlier, I said, hey, how many weights are there in our neural network? And you guys told me correctly. You said, hey, it's around 4,000, which is right. And here are all 4,000 of those weights visualized. So here they all are. And what's really, really cool, I think, right? And let me just walk through these a little bit. So I'm visualizing this first layer of weights as just an image because these weights are multiplied by the image is what really happens. The second layer of weights I'm visualizing just as a line here because it's just, so like this neuron is out, it has 30 output weights and I'm visualizing them here, but you can see the same kind of patterns. And you see that the neurons, when we start learning at the very beginning, the weights just look like random noise, right? So the weights just look like kind of salt and pepper random patterns. And that's because, as you know, we start out with a random initialization, right? But what I think is just the coolest thing in the world, I can't believe this works. So if you look, what do you see happening as the model trains? What patterns, what do you see in these weights? What do you see the model learning? Yeah, road, specifically the lane markers, right? The lines, right? So just by having a signal that tells the model about the steering angle, it's learning to see road patterns, right? Like that's crazy. I can't believe that works. I think it's really fun that this last neuron takes a minute. Not see where this error dips down, right? This last neuron kind of kicks in and starts learning at the end, which is just the funniest thing to me, right? So Why do 3 neurons learn first and the 4th one kind of kicks in later? I have no idea, right? Neural networks can be very unpredictable. But that is how this Alvin network learned in this case. And then finally, I'll just look at this plot with me real quick. So what I'm doing here is the red line is the ground truth. It's the human steering angle. And the yellow line, that is our model, right? So you can see that the more it trains, the closer it gets. It gets closer and closer to the right answer. And that's the idea here. So hopefully that makes sense. I'm just seeing how much phone battery I have left here. 47%. Okay, that's not bad. Okay, learning to steer. I think this is just the coolest thing. And it matches pretty well a quote from Dean Pomerleau. He says, in this paradigm, the data, not the programmer, determines the salient features critical to accurate road navigation. I love this quote, right? I think it really captures how this is different than the approach taken by the ALV team. It's using machine learning. Okay. So let me tell you a little more of a story here. So really for a number of years, from the 80s to the early 90s, Alvin was, you could say, the most successful vision algorithm for autonomous driving in the world. So it really was the state of the art. So here's Alvin in the late 1980s. It had a top speed then of about 1 mile an hour. So here it is driving along. Let me see if, yeah, so this is kind of fun. I like this trivia. So here are the graduate students sitting in the back of Alvin, or sitting in the back of NavLab, being driven by Alvin, the algorithm. And it drove so slowly that actually the grad students would sit in the back and actually program as they drove. So they'd make adjustments and tweaks and train models, I'm guessing, as the system actually drove, which is pretty cool, right? So that's how slow it was, right? It's so slow you could program in the back. Great. So and then I see a quick question: is the training data on GitHub? Yes. Oh, I see what you're saying. So Preetham, I'll get back to your question in a second, Preetham. Good question. Let me just fast forward to the 90s. So in the 90s, performance improved. So Alvin, they built a NavLab 2 vehicle with funding from the government. And this vehicle is able to drive up to 70 miles an hour on highways. You can see it here, fully autonomously. So that's pretty cool, right? So that's huge progress, right? I think that's pretty amazing. So Preetham asked, is the training data on for the challenges the same as what we see here? I believe I've used a different set. I think it's very similar, but I think I've used a different 4 or 5 labs. So the test set on AutoLab is a little bit different than the data set that you have for training. That's on purpose, right? To make sure that you don't just cheat and memorize the data. So yeah, the data will be a little bit different. So yeah, so Sai has asked just a great question. He says, I wonder what NavLab did when the road split. Which way would it go? Yeah, so Sai, this is a great question. This is where behavioral cloning kind of has some trouble, right? Because what should it do, right? What would a human do? What would a human do? It depends on where the human wants to go, right? And that's not really what the model's learning. It's not learning about maps or anything like that. We'll talk about that a little bit later if we have time. But yeah, if the road split, we don't know. Right? It might go one way, might go the other, might go in the center. Might be a fun experiment to try, right? But it's not really designed to handle that. That's a great question. Okay, so I want to share one more thing with you, which is that around 2015, something like that, autonomous driving became very popular again, and it's probably still popular now. I think it's cooled off a little bit, but people have got excited about it again. And NVIDIA, the makers of the graphics cards, they published a paper called End-to-End Deep Learning for Self-Driving Cars. And they really took Dean Pomerleau's idea, which is a great idea, and they really just plugged in a modern neural network. So, Pomerleau trained on about 5 minutes of data. NVIDIA trained on 3,000 hours of driving data. So way more data. And they used a significantly more complicated model. This is an image from their paper of the model they used. I believe I think it's around 100 million parameters, but it's a big deep learning model. These are the kinds of neural networks we'll talk about in the next module, but a much more powerful model. I'm sorry, 125,000 parameters, excuse me. So not as many as I said, but quite a few. So here is NVIDIA's self-driving car, and it's pretty cool. I mean, if you look at these videos, and you can Google these if you want, it does really well. I mean, holy crap, look at this, right? So It's able to drive in the rain on all kinds of conditions. It does great, right? So this is pretty remarkable, right? So this is a fun conversation that I always like to have, right? So yeah, so problem solved, right? Like let's go to production. This thing has learned from data. It can steer a car like a human. Let's put this thing in production cars and let's deploy it, right? So you may have guessed that maybe there's a couple problems that pop up. But on paper, this looks pretty good. We've got this car that's steering itself, and it learned to drive by behavioral cloning. So what's missing, right? You may have guessed that this is actually not how production self-driving cars are working. This is not what Tesla does. This is not really. It's actually not even how Dean drove across the country. Maybe surprisingly. What's missing here? What could go wrong? What are some of the problems with this approach that I've shown you? So safety, sure, there's a whole conversation about safety. So Pooja said unknown road, so maybe, but don't forget, Pooja, that the video you're seeing is that's data that it wasn't trained on. It's not just memorizing; it's learning to steer. So it will do well on roads it hasn't seen. That's a good point. So Hernan, limited data, yeah, sure. Supreet said safety, which I like. You're kind of getting warm, right? Laws, yeah. So there's legality. There's no law that says you can't do this, but it does get a little tricky. So yeah, other drivers' actions, right? So brake and throttle for sure. We don't have that covered. Other cars in traffic. I would like to point something out. So you guys are all, I think these are all great answers, right? So red light, yep. Edge cases, sure. Okay, great. Good. These are all important things for sure. So let me point something out to you real quick. So let's say this exact scenario has happened to me. So we at my last job in the early days as part of our development process to kind of see what technology was out there, just to see it would be viable. We didn't think this could be a full solution, but we just wanted to see what it could do. This was right after the NVIDIA paper came out. And it actually, it worked very well. I mean, I remember driving around the track with this, and I would control the gas and the brake, but the car would steer itself, and it was good. Like, it was a lot of fun. You could go really fast. It was a blast, and it would steer itself. But sometimes, especially after we had it in production not production, but when we did testing for a month or two, sometimes there'd be problems. And there was a certain turn on our track. There's a certain turn on our track where sometimes the car would not actually make the turn. It would fall off the track, right? And here's what I really want to talk to you about. If your boss or your customer or someone came to you and said, how do we fix this? Why is your car not staying on the track, right? What would you say, right? What would you, if this was your solution? So by the way, this approach is called end-to-end deep learning. It's called end-to-end because you're having a deep neural network learn the entire driving process, all the way from input image to a prediction, right? So if your boss came to you and said, why is this not staying, why is this not staying on the track? What would you say, right? So Monica said something interesting already. So Ashish, I really like your answer. You say, I have no idea. So Ashish, I'm not sure if you're telling me you have no idea or you would tell your boss that you have no idea, but either way, that's a good answer. Yeah, so yeah, and so Monica says we have no idea how the car is making a decision. That's a great point. Supreet says, does it try to do better than human driving, learns to make decisions out of data? Yeah, so in theory, it couldn't really do better than humans, really, because it's learning from humans. Maybe it could in some ways, but that'd be tricky. So yeah, this really comes down to a really important concept in deep learning and artificial intelligence. It's the idea of explainability. So yeah, so Videhi says black box. So neural networks are often called a black box, right? And it's because you can't just debug it, right? It's not like other code that you can just debug. It is code, but it's the way it's built, it's learned from data, right? So at my previous job, we were able to improve performance on this corner, but we could never explain. We couldn't explain to anyone, we couldn't just fix a bug, right? Does anyone know? Anyone want to guess how we improve performance on the hard corner? Any guesses? Yeah, just more data. That's it. Just more data, more data. And that's a fine answer. It's okay, but it's still not the same as like giving a guarantee or saying something about how you guarantee that it will do better, right? It's just it's an empirical approach, yeah. So we trained more data, and we actually also did more data augmentation. So we synthetically made our data set appear like it had more sharp turns to help the model learn that better. That's what we did, and it worked pretty well. But here's what I really want to get into. And I'd say if you only take a few things away from this course, this is probably one of the things that I would love for you to absorb and to maybe take into your practice and into your work. And that's that it's the difference between analytical and empirical methods. This comes up all the time. I was just talking about this at work. This happens. This is just a huge concept. So the idea here is that, well, let me just back up. So I've given you some history here, and I've told you about two approaches to autonomous driving, right? The ALV and Alpin. And I guess what I'm getting at here is, at face value, you might say, oh, clearly empirical is better, right? Empirical is better because it drove better, right? But what I really want you to come away with is that for almost any kind of problem solving in computer science, and especially in machine learning, especially in computer vision, there are different approaches you can take, and those approaches will kind of fall somewhere on this spectrum, where there's going to be very analytical approaches that are kind of hand-designed features that are designed by engineering teams or engineers, and there are very empirical approaches that are learned from data. And they each have strengths, and they each have weaknesses. And it's very important, and something I'd love for you to take away from this class is knowing a little bit more about when each strategy makes sense. That's what I'd really love for you to come away with. So here's my summary of it. So analytical methods have some strengths. So they're very straightforward to test and debug. They're modular, so they can be broken apart and tested separately. But they also, of course, have some weaknesses. So the ALV team, they had to make a bunch of assumptions about the road appearance. It's tough to generalize. It can be slow to implement. And for some computer vision problems, there might not be completely analytical solutions. Those might not exist. For empirical approaches, there are some strengths. So this one, for example, makes almost no assumptions. It doesn't rely on specific features. Performance scales well with data. But there's real weaknesses too. So it's difficult to test. How do you know if it's safe? It doesn't incorporate human knowledge explicitly. So we can't tell it anything. We can't tell it if like the road split thing, right? We can't just say, hey, neural network, this is a road split, right? We have to find some training data that captures that, or it's very difficult to add explicit human knowledge the way that I could tell a human driver something. I could say, hey, go right at this split. Neural networks don't have a way to learn that way. And then finally, they're difficult to debug, right? So this is a big trade-off, right? And I think, there was a great question a week ago today. We had a guest lecture with David Deco, and he's a very successful machine vision practitioner. And he very rarely uses machine learning. He will, but his main approach is what he calls discrete vision, which is an analytical approach. And in that industry, for the problems he's solving, like that makes perfect sense. And I'm in that industry too, or a similar industry, and we use machine learning, but we work on different problems for the most part. So I just want to point out that there's different ways to solve problems. And the last thing, what I kind of want to end this lecture with thinking about, and we'll go through some more examples, are that the best solutions to problems like autonomous driving, they blend empirical and analytical approaches. So if I was going to say anything about these two techniques, it's that they're just too far on the extremes, right? You need something in the middle that blends these strategies. And Abhijit says this really well, what about a neural network for each sub-problem? So yeah, Abhijit, that's exactly how Tesla drives, and we'll talk about that. I think we'll have time. We've got about 20 minutes, assuming my phone battery survives. Okay, great. So fantastic. So this again, huge concept. This definitely could be on the quiz. Make sure you feel good about the difference between analytical and empirical approaches. Okay. Great. All right. So let's keep moving. So what I want to get to is this, and based on my battery life of my phone and things like that, we might go a little bit more quickly here. And there's also another video that Arvind has brought up that was a really fun video that I might have a chance to show you guys. So let me just spend a little more time talking about how Dean Pomerleau and Todd Yoakum did this. So It turns out they actually did not use Alvin. So Alvin was a very popular approach, but Dean realized that he would have to be retraining Alvin pretty frequently as he drove across the country. Alvin didn't have enough capacity. He couldn't learn from enough data to let him drive across the country completely. So he implemented an algorithm called Ralph, which is a really, really nice blend of empirical and analytical approaches. Based on my camera dying, sorry, my power going out and my phone dying soon, and the fact that this is not something I'll quiz you on, I think what I'm going to do is I would just like to say that this Ralph approach, what it does basically is a blend of analytical and empirical approaches. And I kind of walk through it here. If you'd like to learn about it, I'd really recommend looking at the YouTube series. In the YouTube series, I talk about Ralph in a lot of detail. And Dean actually has seen it and he approved it. And he said it was a good explanation of Ralph. So it's been approved by the author, so that's good. So I'm not going to spend too much time talking about the exact implementations of the Ralph algorithm, but I would like you just to know that it blends together a learning approach with an analytical approach. So it blends those two things together really well to drive a car. And that's how Dean drove across the country with Todd back in the 1990s. If you're curious to learn more about the Ralph algorithm, please check out my video, read Dean's paper. It's really cool stuff. I will not be quizzing you on Ralph, and you do not need Ralph for the programming challenge. So it's only if you're interested, please go check it out. We have about 15 minutes, and my battery's doing okay on my phone, so we'll see what we can get done. But I would really just like to do 2 more things in today's lecture. So hopefully I've given you an idea for how end-to-end deep learning works, and I've given you some ideas to think about. So I've shown you this algorithm training in TensorFlow. Your job is to train this in Python. That's your job, is to give us some code that will let us train in Python. That's your job before Monday. Hopefully I've told you a little bit about analytical versus empirical approaches and got you thinking a little bit. And we also discussed that Ralph, the algorithm that drove across the country in 1995, was a blend of analytical and empirical. And if you're curious how that blend works, please watch the video series. And then there's just 2 last things I want to do. We might end a little bit early just because I think I'm going to run out of power soon. And I think I'm racking up a pretty big cell phone bill as well. Okay. So I'd like to do 2 things. I'd like to talk about Tesla, and then I'd like to share just one more fun video, and we'll call it a day, and we'll close out autonomous driving. So this is a really cool video that Tesla has shared that shows kind of some visuals about how their stack works. So Monica, that's a nice idea. I can connect my phone to my laptop. That's true. I will do that if it gets too low. Thank you. Good idea. I got to dig up that cable, USB-C and all this stuff. All right, they need to, whenever they put, man, I'm going to be happy the day they put USB-C on the iPhone, right? That's going to be a good day. All right, anyway, so let's talk about Tesla here. And yeah, thank you for that recommendation. So this is a visualization of a Tesla driving. And actually, I have another one I can try to dig up. I'll try to dig that up in a second. Have a look here carefully and see what you see. So neural networks and deep learning are being used very heavily in a Tesla. It's got special computers just to do the deep learning. Can anyone tell me though, so this is not end-to-end self-driving cars. They're using a different approach. And it's also not the Ralph approach either, it's something else. Can anyone tell me what are the deep learning models doing? So throw it in the chat window. What are the deep learning models doing in this Tesla visualization? What do you see the deep learning models doing? Yeah, so Supreet says detecting objects like cars, object detection, yep, and we're going to learn about that in the next module, absolutely. So deep learning is being used to detect the cars, right? And it's also doing some other stuff. But yes, it's being used to detect cars, absolutely. So they're using an empirical approach for object detection, finding the surroundings. You can see these bounding boxes. They're also using it for lane marker detection, finding those. And then they're using analytical methods to actually steer the car. So the analytical methods are actually doing the steering. So that is how, so yeah, why are the green and blue color? Let's have a look at that. That's a great question. And I have another, let's see. I have another video. I'm trying to find it real quick. I was just planning on showing this one, but let's see if I can find it. But yeah, what are the green? So let's see here. It might be coming towards or going away, but actually I'm not sure why they have green and blue boxes. That's a great question. There's one other thing they're doing. So if you see the trees are kind of green as they fly by and the road has these little lines on it, they're doing a technique called optical flow. We'll learn about optical flow in the very last module. It's actually not usually a machine learning technique, but what it can do is it can help you estimate how your vehicle is moving through the world, which can be very, very helpful. That's the idea here. So Tesla is really using a blend of analytical and empirical techniques to achieve this. And I have a couple other decks and things like that. Give me 1 second, guys. We can talk a little bit more about autonomous driving. I know it's a cool topic. And then we'll call it a day. And I'm trying to pull up this video or this deck, but I'm having a little bit of trouble finding it. Let's see here. Yeah, just give me 1 second, guys, and I'll try to pull up one more thing to talk about. This is the main meat of our day, though. So hopefully that gave you a cool understanding of how Alvin works. Yeah, let me see. Give me 1 minute here, guys, and I will see if I can find some other stuff to talk about real quick. There's one video that Arvin brought up that I forgot we showed last year. So give me 1 minute. If I can find it, we'll show it. If not, we'll end a little bit early. So I'll be back in 1 minute. All right, guys, I'm back. I apologize. There's one more video I wanted to show you guys today that Arvin brought up, but I can't find it right now. So if I'm able to find it, we'll look at it. We can look at it next lecture. But hopefully that gives you oh yeah, I'm still sharing this. Okay. So hopefully that gives you a little bit of feel for what's out there in autonomous driving. Today, as we mentioned, there are, a number of companies working on autonomous driving. Tesla may be at the forefront. There's a bunch of stuff we can say about Tesla. Tesla uses vision. There are other companies such as Waymo, which you may have heard of, which is a Google founded startup that's been spun off. And they actually use a very different approach. They don't use as much computer vision. Does anyone know what sensors Waymo uses? Yeah, LiDAR, right? Cool. What's the difference between LiDAR and cameras? Does anyone know what's the big difference? Yeah, depth. So yeah. So LiDAR is an active sensor. Cameras are passive. So LiDAR is actually shoot out like laser beams, right, to measure distances to objects. So in theory, it's a much higher quality sensor. It's very interesting. So Elon Musk believes that he can achieve what's called level 5 self-driving with only cameras. That's an open research question. We'll see if he does or not. But Waymo and other companies in the space, they believe that you need LiDAR or other more sophisticated sensors to achieve what's called level 5 or full self-driving cars. Tesla is a level 2 self-driving car today. So it's very interesting to see how this shakes out. We won't do anything with LiDAR data in this course. LiDAR is not quite computer vision, I would say. It's more of a robotics sensor. It's not quite a vision sensor, but it's very related. So yeah, George Hott says level 3 in 4 years. We'll see. Yeah, maybe. Level 3 is very ambiguous. Like, it's hard to know if you actually have a level 3 system. Audi claims to have a level 3 system. With level 3, the idea is you don't have to have direct supervision all the time in certain constrained domains. No one is level 4. I don't believe Hernan. Maybe Google claims they're level 4. Well, I guess you could say some of the Waymo cars are level 4, perhaps, but they're in very constrained environments. They only work in certain areas of Phoenix. And they do well, apparently, right, from what I've heard. So yeah, it's a very interesting developing area. It's really cool to work in if you're interested. There's lots of really awesome computer vision problems. The safety part is a challenge. How do you know when you're actually driving safely? How can you prove your car is safe, right? That's tough. Actually, I have one more question I'll ask the class, just for fun at the end. So Preetham says, how do you define the levels? Yeah, so there's a bunch of stuff you can read about this, Preetham, but just to give you a quick overview. Let me make sure I get this right. So level 1, that is when you control either the gas and brake or the steering wheel separately. Level 2 is when you control both. If you're controlling gas and brake and steering wheel, it sounds like that's fully self-driving, but the distinction with level 2 is that you have to have human supervision. So a Tesla, it can do the gas and brake and steering wheel. However, legally and technologically, you have to have a human to supervise these things. And unfortunately, there's been a couple of accidents where people have died in Teslas because they haven't been paying attention, right? So the systems do need supervision, and the human is responsible. Level 3 takes away some of that supervision. It's kind of this middle ground. And level 4 and 5 are the fully autonomous driving levels. The difference between 4 and 5 is that in 4, you can constrain what's called the operational design domain, which has to do with where and when are you able to use this car. So the stuff that Waymo is doing in Phoenix, for example, you can only drive in certain geo-fenced areas. So they've constrained the design domain. So that's a level 4 vehicle technically, and level 5 you can drive anywhere. Anywhere a human can drive, that'd be level 5. And level 3 is this really weird gray area where no one really knows who's in charge. But in a level 4 car, you don't need a steering wheel. All right, level 4 and 5 do not need steering wheels, in theory, which is interesting, right? So maybe I'll just leave you guys with this, and it's kind of a fun ethical question around self-driving cars. Maybe it's not fun. I don't know. Let's say interesting. I don't know if fun is the right word because it involves fatalities. So let's see here. So Sai, yeah, let's look at Sai's question, then I'll get into just this last little bit. So Sai says, so to get to level 5, is it more software or hardware? Like more innovations are necessary in the cameras or better deep learning algorithms? Yeah, that's a really great question, Sai. I think a lot of people in the industry would say it's just software, that the hardware is good enough. I think the hardware may be good enough. It's definitely possible, but the hardware is still pretty expensive. The LiDAR unit that we used at my last job was like $30,000. They've gotten a lot more inexpensive, but the hardware is still a little bit fragile and expensive, and it is getting better though. So it's probably mostly software and kind of like, there's another kind of level to it, which is like societal acceptance. And that kind of leads me into my last kind of question for you guys, which is, so let's just take the U.S., but this is a big global problem as well. So, last year I think around 1 million people died in car accidents, which is terrible. It is the leading cause of death of people your age and my age, below 35. It's the leading cause of death in the U.S., I believe. So it's certainly a big issue, a big problem that we would be great if we could find a solution to. Cars are really dangerous. They're just not very safe compared to other things we do. So last year in the United States, between 30 and 40,000 people died in car accidents. So let's say 40,000, just to give us a number. So 40,000 people died in car accidents, which is obviously terrible, and many more across the world. Now let's say that we had a technology, a self-driving car, that could make, let's say it was level 4 or 5, that could reduce that death rate by tenfold, right? So it was 10 times better than humans. So let's say that the fatality rate went from 40,000 to 4,000, right? So you've decreased it by a factor of 10. So that's pretty good. That's a great technology, right? Now here's the thing. If you were in control and you could decide, if you were a policymaker, you could decide to deploy it and you would outlaw human driving. And we're going to switch to autonomous driving, right? So there would be 4,000, instead of 40,000, there would be 4,000 deaths, right? But those deaths are now caused by machines, because those are deaths that were caused by the autonomous car, right? So you've reduced the death rate, but now, like I said, your deaths are not caused by other drivers. It's caused by a machine making a mistake. by a deep learning algorithm or something, some component having a problem. So would you do it if you were in charge for some reason? If you were, you'd have to be more than president, you'd have to be king or something, right? But if you could do this, so just throw it in the chat window, yes or no, would you do that? Is it worth making the trade-off? You're gonna save 36,000 lives, but 4,000 people will be killed by machines. Yeah, really interesting. Yep. So we got, it looks like maybe a little bit more yeses than nos, and we could do a poll, but we're almost out of time. So yeah, so I see maybe half and half, maybe a little bit more no. So it's really interesting, right? So as a society, we aren't really okay. If God forbid someone in your family, died in a car wreck, that'd be terrible. But how would you feel about it if it was, a machine that was responsible? I mean, that's even worse, I think. I don't know why. It's just as humans, it's hard for us to think about that, So that's a real challenge, and the laws around this are still a bit hazy. So it's tricky, right? It's a tricky area, and we'll see what happens. I hope we can make progress, because having this many fatalities is not okay. I don't think that's anything we want to live with as a society. But yeah, what do we do, right? So all kinds of tricky problems, really, really interesting stuff. I think it's a cool thing to talk about, and we'll see what happens. Are trains automated? Yeah, I do not believe trains are automated, probably for the same reasons. You have human conductors, but I think there are more safety checks on trains. I'm sure trains are safer, I believe, and planes are also safer than cars, which is interesting. That's a great question, Monica. I'm not sure. Okay, great. So my phone has made it. That's awesome. And the Ravina, yeah, it's a great question. It's like, 'cause I think this is what bothers humans about this so much, right? So like the 4,000 people who died, they could do everything right. They could be the best people ever. They could be really good drivers, and it doesn't matter anymore, right? That's really tricky for us to deal with. It's just hard morally, it's a hard moral question. So yeah, it's kind of the intersection of technology and ethics. Great. All right, so yeah, Habib's asking about group meetings. I don't know if I'm going to be able to make our group meetings today, guys. I'll chat with Rohan and Arvind about it. If you have a group meeting today, please assume that we will meet. Rohan and Arvind and I will go have a quick talk over text. We'll decide if it makes sense or not. If we're not able to meet today, it may just be you and the TA, probably is most likely. And then we'll have to meet all together later or something. But do assume you're still going to have a meeting. At very least, it'll just be you and either Rohan or Arvind. They know their stuff, and we may have to regroup later. But if you have a meeting today, assume that it's still on. So thank you guys for your time today. I hope you enjoyed the lecture. We had a fun power outage, but we made it through. Office hours should be fine for tomorrow. I assume I will have power by then. If I don't have power by tomorrow, there are bigger problems in the world. All right, guys, have a good day. We'll talk to you next week.